Hi everyone, welcome to the 10th lecture of the series Kalman filter using MATLAB. In this lecture, we discuss some advanced topics and applications of Kalman filter. Here is the overview. We start with the discussions of advanced topics such as extended Kalman filter, extended Kalman filter, and linear quadratic Gaussian control. Then we move on to the applications. Extended Kalman filter or EKF is basically the extension of the Kalman filter to nonlinear systems. In EKF, we consider state estimation of the nonlinear system defined by the state equation as in equation number 1. Here f and h are some nonlinear mapping. Then in EKF, during each time instant, we linearize the nonlinear state equation to obtain the linearized model as in equation number 2, which is then used for the state estimation. Here AK, BK and CK are the system metrics, input metrics and output metrics respectively, which can be computed from the partial derivatives as given in equation number 3. We have already seen how to estimate the states of this linear time varying system using Kalman filter in chapter number 5. So in EKF, we basically follow the same algorithm, with the only difference is that here AK, BK and CK obtained from linearization. The uncentered Kalman filter or UKF is also used for estimating states for nonlinear systems. However, instead of using a linearized model, in UKF, an uncentered transformation is used to update the expectation and variance. The UKF algorithm consists of 3 steps as given here. Let the estimate of the state xk minus 1 hat along with the variance pk minus 1 is known. And our task is to estimate the state xk hat at the current instant. For a second order system, we can represent the estimate xk minus 1 hat as a point in the 2D space and the variance pk minus 1 using an ellipse. Here, the variance matrix pk minus 1 is a symmetric positively definite matrix. And if we consider a set of all points x such that x transpose pk minus 1 x equal to 1, that will be an ellipse like this. The major and minor axis of the ellipse will be decided by the eigenvalues of pk minus 1 and the skewness is decided by the eigenvectors. The size of the ellipse indicates the uncertainty in the estimation of xk minus 1. Now, our objective is to compute an estimate of the state xk hat at current instant and its variance pk using the available information. For that, in UKF, we select a set of points around the estimate xk minus 1 hat, which we call as the sigma points. The first sigma point will be usually xk minus 1 hat itself, and we also select 2n additional points where n is the system order. So in total, we will be having 2n plus 1 sigma points. Now in the next step, we transform the sigma points using the nonlinear mapping from the system model, which results in the transformed sigma points. Then in the final step, we use the transformed sigma points to compute an estimate of the expectation and variance of xk. We compute the predicted estimate as a linear combination of the transformed sigma points, and in the correction step, we add the measurement error time to it to obtain the final estimate. So this ellipse will be characterizing the expectation of xk, which we denote as pk. Note that here if we take more number of sigma points, we can obtain a more accurate estimate of the expectation and variance of the current state. Next we discuss the linear quadratic Gaussian or LQG control. LQG is basically a control algorithm which consists of a linear quadratic regulator or LQR controller and a Kalman filter as the state estimator. In LQG, the control law will be as in equation number 4, in which Kk is the feedback gain, which is computed using an LQR algorithm, and xk hat is state estimate, which is computed using a Kalman filter. So basically, xk hat will be xk given k. The Kalman filter we have already discussed in this lecture series. And to learn more about LQR, the lecture series on linear quadratic regulator can be referred, for which the link is given in the description. Next we move on to the applications of Kalman filter. The Kalman filter is extensively used for state estimation of mechanical systems such as robots, automobiles, aerospace vehicles, etc. In electrical systems, the Kalman filter has many applications in electrical machines and drives, power converters, and power systems, etc. Now, when it comes to medical science, Kalman filters are extensively used for estimating the states of many biological systems. Finally, in economics, Kalman filters are used for prediction and forecasting of the business trends. So these are the major references for this lecture series. The first two are journals written by R.E. Kalman itself, who invented the Kalman filter. For more details about the RTS smoother or the Kalman smoother, this journal can be referred. Finally, these are some of the books that can be used for further reading and learning about Kalman filter and state estimation. That completes this lecture and also this lecture series. And if there is any suggestions or corrections regarding these lectures, please let me know. Thank you.